Today we'll be discussing about the attribute grammar, static semantics, operational semantics, axiomatic semantics, and denotational semantics. Okay. So here we have, of course, discussed before about the BNF and EBNF grammar. But there are some pitfalls in the grammar, right? You can't describe some minute things of the structure of programming language sometimes, right? Using BNF. So where this attribute grammar will help us out. So an attribute grammar is a device used to describe more of the structure of a programming language than can be described with a context-free grammar. It means there are certain issues which cannot be addressed by the context-free grammar can be described with the help of the attribute grammar. Okay. The other way you can say the attribute grammar is an extension to a context-free grammar, right? So for context-free grammar, we have used BNF and EBNF notations, of course. So this basically attribute grammar, as I'm saying, it's an extension to the CFG, which helps you to conveniently describe certain structures of the programming language, such as type compatibility. You know what is type compatibility? Basically when you are declaring a variable as of integer kind, and then at the time of execution, if you are trying to assign some float value, will it take, of course, in C language, yes, because the type compatibility is being taken care by the type coercion, which you call it as implicit type conversion. But if you go for Java doesn't take. It raises an exception. If you declare an integer variable and you're trying to assign some float value for the same, it doesn't take. Of course, vice versa is possible. It means float variable, if you have described, and then you're trying to assign some integer value to the same, of course it takes. Fine. But integer variable cannot be assigned with a float value. So this is a rule rather, right? This is a rule to be declared, while declaring while defining the rules or the productions rather, right? Which cannot be possible with the help of, the BNF or EBNF grammar rather, right? So such kind of things, which you can probably, describe it with the help of attribute grammar. Before you formally define the form of the attribute grammar, you need to clarify the concept of static semantics. Okay, static semantics. So the static semantic of a language is nothing to do with the meaning, but then it indirectly relates to the meaning of the program during the execution. Rather, it has to do with the legal forms of programs. Syntax, it majorly deals with the syntax rather than semantics. As I have mentioned, one example of type compatibility, right? Where in Java, if you have declared an integer variable for whom you cannot assign a float value rather, right? So, which cannot be defined by the CFGs. We are trying to define it with the help of the static semantics, right? So to formally define the static semantics, we will be using, of course, the attribute grammar. Attribute grammar is a kind of concept which probably can be used to implement the static semantics. Or attribute grammars have some additions to the CFGs to carry out the semantics, some semantics like static semantic specification, information on the parse trees, and it helps the compiler designers to check the static semantics. Definition of attribute grammar, right? An attribute grammar is a context-free grammar defined with a twin tuple, right? S starts, S stands for start symbol, N stands for non-terminal, T stands for terminals, P stands for production. So an attribute grammar is of course a context-free grammar, G, which can be defined with a twin tuple S, N, T, P with the following additions, right? For each grammar symbol X, there is a set A of X of attribute values. Each rule has a set of functions that define certain attributes of the non-terminal in the rule. Each rule has a set of predicates to check for attribute consistency. What do you mean by predicate? Predicate is basically a condition, right? An assertion, you can say rather, right? Of course, we'll see with an example what attribute grammar consists of in addition to CFGs, like attributes, attribute computation functions, and predicate functions. Attribute computation functions, sometimes called the semantic functions, are associated with grammar rules. They are used to specify how attribute values are computed, right? So attribute computation functions will be, of course, associated with the grammar rules, which helps us to specify how the attribute values are going to be computed. Predicate functions, which states the static semantic rule of the language, are associated with the grammar rules. Of course, we will make this concepts clear with the help of an example here. Attribute grammar is a grammar with the following additional features, I can say, where you find synthesized attributes and the inherited attributes. Synthesized attributes are used to pass semantic information up a parse tree, while the inherited attribute pass semantic information down and across a tree. Let x0 gets 2 x1 so on up to xn be a rule. The functions of the form s of x0 equal to the functions of a of x1 comma so on up to a of xn defines the synthesized attributes. Functions of the form I of xj equal to function of a of x0 comma so on up to a of xn for I less than or equal to j less than or equal to n defines the inherited attributes. Initially, there are intrinsic attributes available on the leaves, means the terminal nodes rather, right? Fine. We'll see with an example and discuss the same, its terminology rather, right? So here, the syntax of assignment statement is given, specified with the attribute grammar. So here, you can see assign gets 2. When the arrow is towards the right, I say gets 2. If the arrow is towards left, I say gets from. Okay? Assign gets 2, variable equal to expression, and expression variable, equal to expression, and the expression gets 2 variable plus variable, or this is said to be or variable, where variable is defined to be A or B or C. Okay, so now here the actual type in the sense the type of the variable you need to define, right, before the variable being used. Now you can see in C programming language, this attribute grammar is clearly defined, saying that the variables which are being used have to be declared, or the other way I can say must be declared before they are being used, right? So that is set to be the actual type, right, of the variable, right? So you must have to declare the variables of the type of the variables before they are being used. Yes, sir. So the expected type here, consider to be the inherited attributes. What could be the expected type of expression? It depends on the actual type of the variables, right? Yes, sir. So it means here the inherited attributes and synthesized attributes will play a major role in order to define the attribute grammar, right? If you have all synthesized attributes, then you say it is bottom-up approach-based language. If you have all inherited attributes, then you say it is based on top-down approach, right? If there is a mix of both, then you say it's a mix of both, right? Fine. Yes. Now, let us continue this example. The expression which is defined in the grammar gets to variable 1 plus variable 2, you said, right? The expression's actual type gets from the variable 1's actual type. The expression's actual type gets from variable 1's actual type. Fine. Of course, in programming languages, while you have worked with, you may have seen, while you're performing addition, you try to ensure that these variables type also must be equal, rather, right? Okay. But then, of course, the programming languages will take, if they have type coercion into type coercion available with it. Like, for example, in C language, as I mentioned, right? You have type coercion. So if you have declared one variable as float and another one is an integer value, if you're using, the float will be automatically converted into integer value, right? So anyway, these are all being declared as part of the grammar. Only then that is being possible, rather, right? So the type, compatibility issue, which cannot be defined using the normal BNF, can be defined with the help of this attribute grammar, where you are trying to, define the variable's type again, right, in order to get the expression's type. Here, you are going with a predicate, right, in order to conform this, right? You can see what is that you are saying. The condition has to be satisfied. The variable 1 actual type and variable 2 actual type must be equal, right? When you are performing addition on variable 1 and variable 2, their actual type must be same. Yes or no? Right. And then you are saying that, the expression's actual type that you get will be equal to the expression's expected type. It means the actual type, you will be when able to get from the actual type of variable 1, and where variable 1 and variable 2 actual type is same, only then you will be able to confirm that the expression's expected type will meet the actual type of the expression. Yes, sir. So this is the predicate, right? This is the predicate condition which has to be satisfied in order to conform the specification. Okay, so this is how we define the grammar of CFG with the additions using attribute grammar, right? So the expressions expected type. So the expressions expected type gets 2 from inherited attributes rather, right? From inherited attributes, right? So in order to get the actual type of variable 1, how do you get the actual type of variable 1? By looking up A, that is rule 4, right? That is rule 4. Yes. So the actual type of the variable, you get it from this rule, right? It is an ID, right? And this ID must have to be rather declared, right? Okay. So with the respective type. So if the type is A or B or C, then you are going to define the semantic rule for the same, whether it is an integer, real, or any other kind of thing rather, right? So that particular rule will define this variable 1's actual type and variable 2's actual type. Then expression's actual type gets from the variable 1's actual type. And the expression's actual type, whether it is equal with the expression's expected type or not, that is to check the conformity. This particular condition has to be met. The condition which we have discussed, that is the predicate. That the predicate which we have discussed has to be met, right? The predicate must have to be met. Okay. So what is a predicate? This is that predicate, right? This is that predicate which have to be met. Only then the expression's expected type will be equal with the expression's actual type. Fine. This is how you try to define the attribute grammar, where you can probably define the structures of the grammar, language grammar, which cannot be rather defined using the normal context-free grammar. It means it is helping you out to define the, in a little minute manner rather, right? The grammar. Fine. Now, yeah. Now coming to the static semantics, as I have said, static semantic is nothing but to define the structure of the program, which probably relates and helps the compiler to cross-check the variables identity, sometimes type and all right other, which of course does not relate with the meaning of the expression, but rather it helps and then relates with the type of a variable, which we have seen rather, right? As an example. Okay, so now moving to operational semantics, right? So operational semantics basically being used to define the meaning of a particular statement. Okay, like for example, you have a C statement. Okay, you have a C statement. Declare a C statement like this, for example, for expression 1 semicolon, expression 2 semicolon, expression 3. Then you have open brace and you have some set of statements, then you have the closing brace. This is how you define. This is the syntax of the C statement, right? So if you do not have 2 semicolons inside the parenthesis followed by for, that is against the syntax. it will not allow you to write, in the program. It will raise an error as a syntactical kind. Okay, so in order to make the first statement correct with the syntactical rule, this is how you define, right? For within parenthesis, followed by the parenthesis, within parenthesis, we will have two semicolons inside rather, right? So here this expression 1 is generally being used as a invariant initialization rather, right? Invariant initialization, expression 1. Expression 2 is generally a condition, right? A testing condition, the other way around. Yes. This is initialization. And then you have an expression 3, which is generally an increment or or decrement kind, right? With some step of value, rather 1 or 2 or it depends. Okay, so how many times that you want this particular set of statements to be executed, right? This block of statements to be executed, you can control it with the help of these 3 expressions. So the execution of this particular first statement, right? The execution of this particular first statement, or the other way around, the meaning of this particular statement, operation, right, is what's said to be the operational semantics. So here you can see the operational semantics of the same of this first statement. You have already worked with this first statement in C language. The same example I have taken so that it will be easy, it will be easy for you to understand better, right? So the execution of this particular first statement, the meaning of this particular first statement, which is to be interpreted on the machine, is said to be the semantics. I say it is operational semantics because it carries out some operation here, right? Okay, so I say it is operational semantics. Fine. So you can see here the meaning of this particular first statement is, first the expression 1 is going to be executed, right? Expression 1 is going to be executed. Then next what happens? The expression 2, as I said, is a condition, will be checked here, right? Expression 2 will be checked. If expression 2 equal to 0, it means what? 0 stands for false, right? Expression 2 equal to 0 means condition is false. It means you need not to execute these statements, right? These statements which you have mentioned inside the braces, which is nothing but your for block, right? Which is nothing but your for block or this set of statements, okay, to be executed. If this condition is false, what do you mean by it? It means it is true. If expression 2 is true, then what do? You will come here, right? You will execute this. If expression 2 equal to 0, it stands for false. When this is equal to 0, false means this condition is true. Its statement is true. Then what it will execute? It will execute go to out, right? So where do you come? You will come here, right? You will come to out statement. Got the point? Let me make it again clear for you. The semantics of first statement. You have 3 expressions separated with semicolon inside the parenthesis followed by rather, right? So how is that is going to be executed is what the meaning of the particular statement, which is required to be interpreted on the machine, is what I say the operational semantics. So here, what is happening? Here, what is happening is the expression 1 is going to be executed first. Okay, when this condition is false. Okay, when this condition is false, you will terminate the first statement. You will come to the next statement rather, right? Next statement. So when this condition is false, you say go to out, it means you will come to the next statement, right? Otherwise, you will be executing the block. You have this block, right? Which is nothing but the for block, I say, are the set of statements which you have put inside the for to be executed for a repeated number of times, right? And then after that, you have expression 3 here, right? This is expression 3. Expression 3. So expression 3 is generally an increment or a decrement kind of thing, which is going to be executed, at the end of every iteration, right? At the end of every iteration. So it means expression 3 is going to be now executed. After then, again, where do you go? You will go to loop. It means you will come for this state. It means again you are trying to execute the next iteration. Before executing this, next iteration, what is that you're going to do? You will be checking the condition. If the condition is true, then you will be allowed inside this block and you'll be executing all this, and then the expression 3 will be executed, which helps you to increment or decrement. Then you go to loop. Okay, then you go to loop. How long you do this? Until the expression 2 equal to 0 is true, it means this particular condition is false. When this condition is false, okay, when this condition is false, where do you go? You will go to out, right? Where is out? Out is the next statement. Fine. So the meaning of this particular first statement is being defined with the help of the operational semantics, right? The way in which this particular first statement has to be understandable by the machine is what the semantics, right? Semantics is nothing but the meaning of the statement. How has to be understood by the machine, right? So this is about operational semantics. I've given you an example. I hope it is clear to you. Now the next topic under the same, I said axiomatic semantics, right? So axiomatic semantics. Axiomatic semantics defined in conjunction with the development of a method to prove the correctness of program. Language of axiomatic semantics is based on predicate calculus, right? You have some logical expressions as a, like mathematical logic, okay? Or you can call it as assertions, like preconditions or postconditions. One example here I am trying to discuss, right, of the same. In order to execute this particular statement, okay, in order to execute this particular statement, sum equal to 2 into x plus 1, what could be the precondition and postcondition? Let us say postcondition is given. Okay, postcondition is given. What he is saying, when you execute this statement, you must have to get some value greater than 1. When do you get the some value greater than 1? After you execute this, when there is some variable, you have x, which must have to take the values which will enable you to give this particular result. Fine. Constant doesn't make or doesn't play any role here, only the variables. Here you have x. So what could be the x value when you take, you will get some value greater than 1. If you take, even 1 you get, because 2 into 1, 2 plus 1, 3. If you take 2, you get rather, right? Fine. But when you take 0, you don't get the value of sum greater than 1. It means you will not be able to meet the post condition, right? So the value of the x must be greater than 0. This is the weakest precondition I can say. Well, if it is greater than 0, it means if it is 1, x equal to 1 will be the weakest precondition. But x greater than 10 is also a, I can say is a precondition, right? I can take x value to be higher, greater than 10 or 100 or 500, no issue, right? But the weakest precondition is what could be the least value, right? Least restrictive precondition, which guarantees the post condition is said to be the weakest precondition, right? Weakest precondition is the least restrictive precondition, which guarantees the post condition is said to be the weakest precondition, right? So, if programming language is adopting some axiomatic semantics in order to conform certain statements based on certain assertions like preconditions or post conditions, then axiomatic semantics will be used, right? Now coming to denotational semantics. Denotational semantics, generally some mathematical equations, okay? If you have mathematical representations, then you can probably use denotational semantics. It is based on recursive function theory, right? The most abstract semantic description methods you have defined in denotational semantics. This is originally developed by Scott and Strachey in 1970. We'll see with an example here. Like for example, if you are trying to define the decimal numbers, okay, decimal numbers. Decimal numbers will have how many digits? Will have 10 digits, right? 0 to 9. 0 to 9. But then, if a number is having more than one digit, right? One digit, more than one digit. This, let us say, this is the mathematical representation, right? Generally, we use a recursive function only, because this function is the atomic function, I can say. The decimal number consists of 10 digits. And now, in order to define 2 digits decimal number, let us say, okay, or more than 2. How do we define? With the help of this definition, right? So, the decimal number carries decimal number 0. What do you mean by this? You have one digit here. This digit could be 1, 2, 3, 4, 5, anything. And then you have 0 in the ones place. This is ones place, this is tens place, right? So, in order to execute this particular statement, how do you define the grammar? Fine. This, you have to define the grammar for this particular decimal number, right? So, how do you define? This is in the 10th place, so you say that 10 into m decimal of decimal number, right? Because this 0 anyway, even if you add, it doesn't matter, right? So, we are not adding it, right? You just say 10 into this decimal number. If this decimal number is 1, then it is going to be 10 into 1. If it is 2, then 10 into 2. If it is 3, 10 into 3, like that, right? And this 0, even if you add, doesn't matter. But when, let us say, you want to define the grammar for 2 decimal digits where the first position, one's position is having the decimal digit value as 1, then how do you define the grammar for the same? You define like this: 10 into m decimal of decimal number plus 1, okay, plus 1 must be added. So if you have, let us say, 2 and 1, 21, then how do you define 10 into this 2, 20, 10 into 2, 20 plus 1, so it's going to be 21, right? So like that, you are going to define the grammar. So this is for 2 digits. Similarly, you can define it for n digits, right? Only thing is, this function has to be repeated, right? This is going to be repeated, right? For the subsequent digits, right? So this is how the denotational semantics are being used in grammar to represent the mathematical rigorous functions, and they will be defined with the help of recursive functions majorly, rather, right? So if I see the differences between the axiomatic semantics and the denotational semantics. Okay. I can say in operational semantic, the state changes are defined by coded algorithm. You will be defining the algorithm, right? What must have to be executed first and how it has to be executed. Here, we have seen with an example of first statement here, right? It's a kind of program only rather, right? It's a kind of program. Here you are executing expression 1 and then you are checking, right? Expression 2. If it is, true, then only you are allowing the statements to be executed. Otherwise, you will be going for the next statement, right? So for this, you need to program. It means it's a coded. You can say it's a coded algorithm. Whereas denotational semantics, the state changes are defined by rigorous mathematical functions, right? Which can be implemented with the help of a recursive function, which we have seen as an example, right?